All right, well, thanks everybody. Great to be opening reInvent on this Monday morning. So we're going to talk today about chaos engineering, and I'm going to also bring up Anna Modena pretty soon. She's going to cover a bit in the middle, some sort of hands-on demos of what it looks like, and I'm going to give you more of an overview of what chaos engineering looks like, why we care about it, and some sort of where this is probably going to be going. So I'll be doing history and future, and Anna will be actually breaking some containers. So here's a few questions. What should your system do when something fails? You really got a few choices. Well, collapse in a heap is one choice, right? That's actually quite a common choice that people make when they didn't think about what might happen when something fails. But you really got two choices. You get to stop or try and carry on with reduced functionality, meaning that you've figured out how to mitigate that failure and keep going. Sometimes the right thing to do is stop. Like if you're not sure whether it's the right thing to do to move $1 billion from point A to point B, you should probably stop. If you're not sure whether somebody's authenticated and should be able to do, watch a movie for free, or, that doesn't really cost much to do, you should probably just let them keep going. So, do you have a backup data center? Who here has a backup data center? Let's get some interactive audience participation here. Okay. How often do you fail over apps to it? So you get the embarrassing silence here. One of the good answers is about once a year because the auditors make us do that, right? So how often do you fail over the whole data center at once? Someone goes and hits the power plug or, no, really, people very, very rarely do that. So I call this availability theater. You built yourself a whole new backup data center, and you're too scared to actually practice failing over to it, and it's a bit like taking your shoes off at the airport. It makes you kind of feel more secure in some weird way, but it's really a psychological prop at this point, or maybe it's because the auditors made you do it. So we have this fairy tale. Once upon a time, in theory, if everything works perfectly, we've got this great plan to survive the disasters that we thought of in advance. Unfortunately, it's not a good fairy tale if you want to sleep at night. Don't try this on the kids, because it really doesn't work out well. Here's a few cases where that didn't go very well. How about, think about what would happen if the primary domain name for the company you work at, somebody forgot to renew it. Like, how much stuff would still be working? So this actually happened a year or so ago. What was left of this company was the CEO apologizing on Twitter for about a day until they figured it out. So don't be those people, right? Everyone's going to think about, oh, damn it, how do I guard against that in the future? If anybody hasn't seen this problem, then you probably haven't run anything for a while, right? Everybody has seen a cert timeout. They just do it. We've built elaborate schemes. When I was at Netflix, we built schemes for just tracking certs, and one of the monkeys would sort of complain at you if it looked like it was running up. AWS, we check all these things. We have how many days left for all the certs we can find. So this is another thing. Every now and again, one of the certs you didn't notice will time out and take you out. Turns out computers don't work well underwater. So kind of one of those things. And when the water goes away, they don't work when they're full of mud and sand and bits of seaweed either. So, a friend of mine had to deal with this. It was unplanned. He spent quite a few months rebuilding a data center. Not a good plan. So the problem is, this could be you tomorrow. Not to start off the week with the downer, but think about all the things that could go wrong. And you can't really predict everything that could go wrong. So here's some of the best advice I've heard. Chris Pinkham was one of the early, he was the original engineering manager for EC2 more than a decade ago. And I was on a panel with him ages ago, back in about 2010, and he came up with this thought, which I thought was one of the sort of really, really key ideas. You can't predict exactly what will go wrong, but you can get very good at detecting and responding quickly. Right? If you can detect and respond quickly, you can limit the impact of anything happening, because the next thing that happens is likely something that's never happened before that you didn't prepare for. It's the one weakest link thing. So, a few more things to read. The network is reliable. Of course, it isn't. This is a great paper on ACMQ. It lists all the ways networks aren't reliable, all the things that look like network partitions. And these are great. Peter Bayliss and Carl Kingsbury are definitely worth following if you want to go follow up more about this. Another thing, even if you do everything perfectly at every stage in the process, you can still end up with a catastrophe. And if you can't understand how that happens, then this is a great book to read. I tell people to read this book, but don't read it on a plane, and don't read it if you have a loved one in hospital. I think, unfortunately, that means very few people read it, because I actually ended up doing a whole conference keynote earlier this year where I went through chapter 2 of it, which is kind of sobering, because it's an end-to-end plane crash. But you can go find that. It was a Go to Chicago talk. You can have a catastrophic result after optimizing every step in the process and doing nothing wrong. This is a really, really profound thought you have to think through. The first edition of Release It by Michael Nygaard was a really formative book. Lots of great information there, lots of ideas about circuit breakers, bulkheads, and the second edition has a whole bunch of new ideas in it. So if you've read the first one, get the second one. If you've never seen this book, it's a really essential book for getting software in production reliably and all the things you can do to make that work well. So this is chaos engineering. This is the principles of chaos, and the discipline of experimenting in a distributed system in order to build confidence in the system's capacity to withstand turbulent conditions in production, which is a bit of a mouthful. So I'm going to boil this down a bit. Key things. It's experimentation. You're running experiments. You're trying to build confidence, and then there's this capacity to withstand turbulent conditions. That's a bit of a mouthful. So I'm going to modify this a little bit to be something that I think is a little bit more boiled down, and this is, the terms here are a bit more precise. We're experimenting to ensure that the impacts of the failures that are going to happen anyway are being mitigated. Right? And these terms have very precise definitions in control theory and engineering. We understand what failures are, we understand what mitigation is, we understand what experiments are. The turbulence is something that's really a different concept. So I think this is a better way of stating it that lets us boil down what we should really be doing. So here's the thing. What went wrong? What kind of thing failed? What are the effects of the failure? What mitigation mechanisms do you have in place? And the problem is you're only going to be as strong as that weakest link, and it's difficult to think of everything that might fail. But the more things you think of, the better place you're going to be. You're going to push the types of failures you get out into those Byzantine, complex, weird things you've never seen before, rather than being the obvious thing that should be staring you in the face if you thought about it for 5 minutes. So you can clean up the easy stuff. The hard stuff will never go away, but it's worth cleaning up the things that you can. I did a version of this talk that's a full hour. I did it at the Chaos Conference, where Anna also presented. You can think of this presentation as two 1-hour talks from that conference sort of mashed together into one talk for here. So if you want to see a lot more detail on the taxonomy and a lot more of Anna breaking containers, you can go find the Chaos Conference from last September. But I proposed some terminology for the different ways you can categorize failures. And I put them in these layers. At the bottom, there's infrastructure failures, like a disk breaks, a network fails, those kinds of things. Above that's the software stack, the things you brought in, the stuff you downloaded from GitHub, the packages you bought, the things that you didn't build yourself. That's what I think is the software stack, all the different ways that can fail. Then there's the application code that you wrote. There's lots of ways that can fail. And finally, on the top, even with a perfectly good system, if you operate it incorrectly, you don't give it enough capacity, or you don't do an update correctly, there's lots of ways from an operations point of view that you can also cause failures. So think about all the different kinds of things that can go wrong at all these 4 different layers in your stack, and then break it out. Just have sessions where everyone gets together on a whiteboard and says, these are all the things that could go wrong, how probable are they, and what's the impact going to be, and what can we do about them? One of the most fundamental things we do when we're trying to figure out how to mitigate a failure is we have to deal with state. And the state, in order to mitigate it, has to be replicated. You have to have at least 2 places where you can have your data, and at least 2 ways to get there in order to have a really reliable system. And there's multiple levels you can do this at. Obviously, at the bottom level, sort of the traditional data center SAN level, there's sort of storage block level replication, or on AWS, it would be something like S3 or moving snapshots around. Above that, you've got a more structured level where the database itself knows how to do replication. So there's a lot of options in that space. And at the top level, in your own code, you can figure out, well, I can send all my traffic, my incoming requests to 2 different places, and I can process them in parallel. There's a number of ways you can do that, or you can embed recovery and failover in your application as well. So there's 3 different layers to think about how you want to do that. Now, if we think about where this came from, I'm just going to do a bit of past, present, and future. So in the past, we had disaster recovery. That was me talking about earlier, asking, so do you have a data center? Do you ever fail it over? That's the kind of disaster recovery model. Now we have chaos engineering just emerging as a new topic. It's becoming quite interesting in the last year. More and more people using it as a phrase, as a little meme to kind of have a rethink of how we're going to do disaster recovery. And then in the future, we're going to be looking at really resilient critical systems. And the key thing here is, I'm sure many of you are moving operations from the data center to the cloud. If you think about when that happens, we're not just moving the top-level applications, the ones that the new greenfield applications. If we start shutting entire data centers, you're getting into the back-end systems, the core banking systems that move trillions of dollars around, the safety-critical systems that keep aircraft flying or keep industrial machinery operating or that keep your business running. When those move to the cloud, the cost of failure is much higher. So we're now at a stage in the cloud where more and more people are moving more and more critical things into the cloud. And this is an area I've personally been working in and working across a whole group of customers in the last year or so. So I'll talk a bit about what that might look like. So here's the history of this. You may not realize there was a company called SunGuard, and it was the Sunoco, the Sun Oil company, and GUARD stood for something like Guaranteed Application Resiliency or something like that. And that was really where disaster recovery came from. It was mainframe batch oriented. They wanted to fail over their batch jobs so that people would get paid when the data center was having a bad day. And they defined these two terms, recovery point objective and recovery time objective. It's very simple to think about if you think about a daily backup. That means you have a recovery point of once a day. Anything that happened after the backup, between backups, is lost. So you lose up to a day's worth of work, but you get back to wherever you took your backup snapshot. And you can obviously shrink that time down to be shorter and shorter periods of time. Once you get into the milliseconds, then you can say, I have an RPO of 0 if I can replicate the data into more than one place before I acknowledge the request, right? Sort of a distributed transaction. And RTO is how long it takes. So maybe you have a daily backup, but if you try and restore from the backup, it might take you 2 days to get it back, the machine back up and running, right? So they're not really related. It's how fast can you recover after you've noticed something's gone wrong. So 2 different numbers here that we characterize most of these availability systems by. And this is the whole business continuity. There's a whole industry around this. There are ISO standards around it. One sort of plea here, if you're working in this space, try not to reinvent terminology and practices that the industry's been working on for a few decades. Read the ISO standard, read the glossary. There's a really good definition of a whole lot of terms. There's a lot of business process kind of stuff that really doesn't need to change. We're changing the underlying technology with chaos engineering, but what we're really doing is re-engineering what's been happening in disaster recovery for the last few decades. So what is chaos engineering? Where did it come from? So some of you may know Jesse Robbins. He was at Amazon years ago. He called himself the master of disaster. He did go into data centers and hit the power switch. He was that guy. One time he actually was even more devious. He's also a part-time, he's a reserve fireman. And he went in and he simulated a data center being on fire. So he didn't just hit the power switch. He said, well, if the data center was on fire, this is the order in which things would go down. And he simulated that. This is within the Amazon retail site in the early 2000s. So when I was at Netflix in 2010, we were looking at moving to AWS. We were trying to think, how were we going to build something where we wanted a TV set to just behave like a TV set normally does. You shouldn't have to think about whether the internet's still working if you want to watch something on TV. That was the underlying principle. We wanted it to be seamless and highly available. And Greg Ozell, whose Twitter handle is Chaos Simia, which is a bit of a giveaway, he built the first version of Chaos Monkey and hacked on it a few times. It was the first thing we installed in the cloud when we launched. This is a really important thing. If you're launching a new application, put the chaos in there first. Build it into your system before you install any apps. It's much easier to install an app on top of a system that's got chaos processes in it, because you'll find the bugs then. And it's almost impossible to add chaos to a running system, right? You will find it's just too fragile. So it's much better to start from scratch in the cloud and build your chaos principles in, and then bring your applications along later. I mean, it'll always help, but to really get to the kind of resiliency that we need to build the chaos in early. By 2012, Netflix, I helped create the open source program there, and we open sourced the Simian Army, a whole lot of chaos monkeys and things like that. And Colton Andrus, who was at Netflix and at Amazon before that, left and formed Gremlin in 2016. That's where Anna works, and she'll tell you more about that a bit later. The Chaos Engineering book came out last year, and there's also an open source project called the Chaos Toolkit if you want to play around a bit with some open source tools. And we're starting to see it adopted more widely, and we're seeing it at many more conferences nowadays. So just to summarize, I think of this as 4 layers, 2 teams, and an attitude. And the 4 layers are people, application, switching, and infrastructure. So you want to exercise the people with game days. You want to know what to do when something goes wrong. The application layer is where your code shouldn't just fall over if it gets a timeout, right? There's a lot of things where you just haven't really tested it under any duress. You need some switching between systems. So if you're trying to fail over between 2 regions or zones or 2 copies of an application or 2 data stores, you have to have a way to switch between the 2. That switch has to be more reliable than the things it's switching between. Otherwise, your overall reliability will go down. This is a core principle of reliability engineering. If you're switching between 2 things, the switch has to be an order of magnitude more reliable than the things you're switching between. Now, if you think about your disaster recovery failover processes, you probably test them so infrequently that they're one of the least reliable parts of your system. So this is a big problem, and this is one of the core things that chaos engineering is trying to get at. It's to exercise that switching so that you know that when something goes wrong, the system's going to do the right thing. And at the bottom, you need replicated infrastructure. And you have the chaos engineering team working on this. I haven't got time to talk about it today, but the other team that I think is interesting is a security team. Some of you may have a red team in your security operations. The red team's job is to break into your system. They work for you, so they're not going to really steal anything, but their job is to test your security by trying to break in. And the chaos engineering team is testing your availability by trying to find the weak parts in your system as well, right? In the same way, the security team is not trying to actually cause a public breach as they do it, right? The chaos engineering team is also trying not to cause a public outage of your system as they do that. They're just trying to find the weak spots. So failures are a system problem. It's not something with the root cause of component or human error. Its root cause is a system inadequacy. It means you don't have enough capacity in your system. So when you're doing root cause analysis, you should always try to drive discussion of root cause. If it starts to get into somebody did something wrong, you're going in the wrong direction. You should always think about what in the system is inadequate that didn't prevent this problem from happening. That way your system gets better and better, you get a more and more robust way of operating. So what we're doing is we're making hypotheses that say, I think we have a safety margin, let's test it to be sure, right? We're doing it in production, and we're doing it without causing an issue. And there are some people that says, I don't want to do chaos in production. I'm going to do chaos testing in test, I'm going to do resiliency engineering in production. Well, it's fine. If you want to call it that, it's fine. It's the same thing. We just called it something different so you didn't have the word chaos near production, and that makes people more comfortable. I don't care what you call it, as long as you are actually testing failure modes in production, right? So these are the outcomes. These are the 4 layers we want. We want experienced staff. They know how to be on call. They know what to do when there's an incident. They know how to log into the dashboards. They know how to get in and modify and fix things, right? That's the experienced staff part. They've been through some game days. You have robust applications that don't just collapse at the first sign of anything going wrong. You've got a dependable switching fabric, and you've got a lot of redundancy in your service foundation, including redundancy of data sources. Data is in multiple places. So let's look at this in practice, look at some mechanisms for AWS and for Kubernetes. The AWS Isolation Model is based on having no global network or service dependencies. It's kind of inconvenient that AWS doesn't have a global network address space, but it's deliberate. It's because you can screw up a global network address space. And if you break something, you only break it in one region at a time. The regions are completely independent. Regions are made up of availability zones. Zones are 10 to 100 kilometers apart. That means they're in separate floodplains, they're on separate electric supplies, they're on separate connections to the network. But they're close enough for synchronous replication. So this is a key part of the model that AWS built in the early days. We want to be able to do synchronous replication into two places that are far enough apart that they are going to be independently available. You know, that flood thing where Hurricane Sandy floods one data center. If you're using two regions on AWS, it's basically they're far enough apart that the tornado or the hurricane or the flood aren't going to hit the same place. But they're so they've got to be close enough, a few milliseconds apart, which is within enough latency to get the replication to work. Zones are made up of normally multiple buildings, because we're getting pretty big now. And the data centers, each building itself is actually broken up internally to multiple sections. So a failure in one part of one building at AWS doesn't take out the whole building or the whole zone. So we have other levels of containment, particularly for the critical services. You know, I think tonight there's a keynote tonight where you'll hear a lot more about how AWS infrastructure works. I encourage you to pay attention to that one. And we have a redundant private network that goes all the way around the world. Here's an actual mechanism. This is a neat trick. You can get inside Aurora, which is our replicated database. And you can get in there, and because we're managing the back end for you, you can't really just get in there and mess with the underlying machine. So we give you these abilities to simulate certain types of failures. You can crash a master replica, failure it, cause disk failure or congestion. So you can say, what happens to my database if I actually inject these types of failures to it? And there's just one example here. Another mechanism, if you're doing multi-region and you want to simulate what would happen if a region, if a particular service in a particular region is no longer available, then you can actually introduce that failure at the IAM level by having a permitted list of regions and dropping one from that region, dynamically. So it's not really what this region scoping thing was built for, but it gives you a way to actually mess around a little bit with multi-region access and what would happen, say, if I want to block all S3 writes to a particular region, I can go through and modify the IAM roles to take that permission away while my application's running. And for Kubernetes, you have all of these different regions and zones that you're running in. This is 3 zones in a region. And within Kubernetes, you have a control plane, a set of master nodes, and you have a series of nodes which are running your containers for you. So you can impact the control plane directly. You can get in there and try to say, okay, what happens if I lose a copy of etc.d or I lose one of the Kubernetes daemons that's running my system, maybe an Istio daemon. There's a whole load of containers which are there running the various layers of systems that you're running in a Kubernetes environment. So what happens if you lose each of those? How long does it take to recover? Or you can go in there and impact the actual applications as well. So I'm going to go on now to talk about Gremlin, but I'm going to move over to have Anna come up and run through what Gremlin does and talk through give you a few demos of how to take out a few containers. All right. There you go.
Thanks, Adrian, for that overview on chaos engineering. It was really good. So now is the fun part. I get to show you guys a little bit of breaking containers, which is always fun to say, too. So my name is Anna Medina. I'm currently working at Gremlin, and I'm doing chaos engineering there. So a little bit about Gremlin. We're a chaos engineering platform for enterprise. We offer 12 Gremlins out of the box. If you want to do chaos engineering on experiments, you can run resource attack. That includes maximizing your disk, your CPU, your I/O. When talking to companies about different outages that they have, there's always that talk that's like, hey, our disk filled up and we had this outage happen. So even just thinking about small scenarios like that really makes a difference. We also offer network attacks. That includes dropping packets, injecting latency, black holing all traffic to a certain port or application, or messing around with DNS. There's also state level attacks, and that would be killing a process, or what happens if my host dies, or if I kill a container. And if you're running serverless, we're also doing application level fault injection that you can also implement that way too. You're gonna see our UI that I'll run through with a demo today, but if you're also interested in maybe implementing this into an internal tool that you already have in place, there's an easy to use API as well. So to start off, Adrian kind of like gave a good overview of how chaos engineering has to do with experiments. But you can think about it the same way that you did experiments as a kid, where you come up with a hypothesis and you start thinking about what you actually think is going to happen once you start doing the experiment. But for chaos engineering, it's a little bit different. You also have to start considering abort conditions. What is going to make me stop running this chaos engineering experiment in case something goes wrong? Since we're injecting failure, you need to be extremely careful. And in the case that your experiment ends up with one of those abort conditions, you want to go ahead and stop that experiment immediately, and then go and fix that issue, and hopefully be able to run that experiment over again and see it succeed. And once an experiment is successful, well, you want to go and now scale this experiment. So what does that actually mean? Well, why run a chaos engineering experiment on 20% of your infrastructure if you actually don't know what this experiment is going to do on 10% of your infrastructure? So this is what we like calling blast radius. Blast radius is where you're able to start really, really, really small, and as you see your experiment be successful, see your services, your applications be able to sustain this failure that you're injecting, well, now you go and you can actually expand that blast radius. So this means maybe run on one host, run on 1% of your infrastructure, and you see that experiment go well, do it on 25% of your hosts and things like that. But this also means thinking about where you're running these experiments. So it would be awesome to just be able to walk in on Monday and be like, hey, I want to do chaos engineer experiments now. Let's go. Let's do this in production on all of our fleet. Well, you probably won't get buy-in from anyone, and this actually might cost you your job. So I like thinking about, hey, what happens if we start doing chaos engineering first on dev, test, QA, whatever other environment you have in place that is close to production. So you still have to think about the blast radius, even if you're not necessarily doing production as well. And that also includes just because you don't want to do chaos engineering experiments to break your test environment. You don't want to piss off all the developer tool engineers by breaking their stuff as well. So let's see this in play. So for today's demo, we're going to be using EKS. We have a cluster set up, and I also decided to run with something that you can take home and play on your own too. So I ran the EKS Getting Started guide, and this lets you set up a guestbook application with a Redis primary and 2 replicas. I've also gone ahead and installed Gremlin, but the one thing that you need to remember is that the #1 prerequisite for doing chaos engineering is that you need monitoring and observability. Don't run chaos engineering experiments if you don't know how your systems are doing currently. And why run a chaos engineering experiment if you can't monitor how it's going as the experiment goes on? So that's also the cool thing with some of the monitoring tools out there. You're also able to automate it that in case you have a certain threshold, a certain alert that goes off in your monitoring, you're able to call your chaos engineering platform and stop that experiment immediately so it doesn't continue causing more impact or possible downtime. So for the first experiment, I'm going to be doing packet loss. And we're going to be dropping some packets on the guestbook containers. My hypothesis is that when packet loss happens, I expect a degraded user experience, but I'm kind of unsure what that means. And I currently want to think about be really inclusive and think about all my customers. So what actually happens to those customers that are running in countries that the network is not as reliable? I want to see what they would experience using this guestbook. And for abort conditions, I've decided to say, I'm going to stop this experiment if I see any data loss or HTTP 500 errors. There's a whole bunch of other abort conditions I could have also put on there, but keeping it simple for today. So on the right, we have our simple guestbook UI application. I've gone in, just added some names, decided to do a reload to make sure everything is good. So on the left, we have our Gremlin UI. We go over to the containers. Gremlin plays really well with the AWS tags, so it completely imports that. So I'm able to come, choose all my guestbook containers, and now I get to choose the attack. So going over to the network layer, I get to choose packet loss, decide to run a packet loss attack for 60 seconds, and I want to drop 20% of the packets. So the experiment has been started. It takes a little bit sometimes to start, and then now I want to see what that experience would be on the UI. So I go in, start putting in some names, and experience starts to get a little bit slower, but still kind of usable. You see the user input return on the UI, which is good. With the reload, we see there's a waiting for database connection, not much info, but things loaded up again. So things didn't completely fail, which was good. So thinking about blast radius, now what actually happens if I decide to increase that 20% to dropping 50% of the packets? So going ahead on the UI and going to select my guestbook containers, choosing my network gremlin for packet loss, and doing 50% dropping of packets. So kind of expect the user experience to be a little bit degraded, but I also don't know how much more degraded it will be than when I ran that 20%. So start inputting some extra names. I see it's still slow, kind of like what we saw previously. Of course, the delay is a lot longer. And I just kind of want to know what actually happens to my entries as I actually don't get to see them in the UI. So refresh, wait, and I start noticing that even the responses that weren't showing up early are actually starting to show up. So there is no data loss on the entries. So if a user is able to submit information, it still managed to get to Redis, and things worked out well. So now I know a little bit of how that acts. The results were as expected. The user had a degraded experience, and that's okay. But I want to make that better. And some action items I thought about is like, hey, maybe I can actually have a little bit better error messaging. So waiting for database connection doesn't really tell anyone much information if you're like a non-tech savvy user. And at the same time, kind of like want to know what actually happens if I drop 90% of the packets. What if that internet connection is so unreliable, but I want to know how that user is able to shop my store, be able to browse my website. So thinking about that inclusive customer experience is a good thing. For the second experiment, I want to run something very similar. I want to run a latency attack. I want to inject 2,000 milliseconds of latency into my guestbook containers. I'm also going to run it for the default 60 seconds. For this, kind of like how the packet loss, I have the hypothesis that with added latency, the application will be a little bit slower, but still usable by the user. So the exact same experience that we kind of saw with packet loss. Same abort conditions of data loss and HTTP 500s. So we go ahead and add some more user input. We go ahead and create the attack, go over to containers, look up our guestbook containers over again, be able to select them all, and choose the latency gremlin. We go over and we decide to inject 2,000 milliseconds of latency. And we get to start that attack. And now I can go over to the UI and actually see what goes on. So start inputting information, see a delay, somewhat expected, but you could kind of see like, it's kind of like giving you like, I'm processing, but not telling you much. And you still don't see the entries after like 1 or 2 seconds. So this can actually lead to a user doing a double entry, or if you're an e-commerce site, they can actually be making a double purchase. And with those purchases, the credit card transactions also get started, so you also might be getting a customer quite mad. So I actually just want to go ahead and stop this experiment. I didn't think that was actually meeting the SLA, SLO I had in place, so I can easily just go ahead and stop that. And kind of as expected, the application, well, actually not too expected, the application did not give the user a usable experience. They weren't able to necessarily get a UI that responds back to it as they were interacting with it as I would like. So thinking of other action items that I can come up with apart from the ones that I also came up with packet loss, well, what if I actually insert like another caching layer and be able to display something on the UI while the latency is currently going on, so that way the user is able to see some information versus just seeing like an empty page that says waiting for database connection. So for some companies, this means being able to degrade the experience as you see some packet loss happen, some latency happen, be able to not necessarily show like the continue watching now, or these are the top movies. So think about the inclusive experience for everyone. So for the next experiment, I want to shut down a container, and that's going to be the Redis primary container. So what actually happens if I kill my Redis primary? So I think if I kill the Redis primary, the Redis replica will just get promoted to primary and things will continue like running smoothly. I think that I'm gonna have the same abort conditions of data loss and HTTP 500s. So let's see that in play. We're gonna go ahead, put some user input again, and then go over to Gremlin, create the attack. It's going to be a state attack. We're able to select now the Redis. We look at the tags. We see the master and the two slaves, so primary and replicas. And the shutdown, we want to make that delay 0, so it just happens automatically. For a container, doing the remove doesn't do much, since Kubernetes brings it back up, which is actually pretty cool. And now we get to go to the guestbook. And let's put some user input, see what goes on. Oh, we just actually lost the information that we had, which is not necessarily anything you would ever want to have. Data loss is extremely expensive for any type of company, whether you're a bank, e-commerce, or just hosting any user information. So being able to actually test something out of the box, just being able to play with it, is actually like one of the cool things with chaos engineering. So the results were actually unexpected. The Redis replica did not get promoted to primary, and data loss has happened. So my action items, of course, would be like, hey, let me go look into why this Redis replica did not get promoted into primary, or what actually went on. So when I decided to look into this, well, we see that the information for the Redis replication is actually set up properly. We look on the left, we have our primary, we see that they have 2 replicas, and we look at a replica, and it has a primary. So in theory, everything should have been working fine, but with more digging on, Redis doesn't provide that out of the box for you. It's not one of those things that you can automatically get that. But how do you know that when you're actually just looking at technologies you want to implement to your company? You don't until you actually are able to inject failure. So that's where chaos engineering is really cool. So for Redis specifically, for Kubernetes, there's various ways you can do it. You can do it like via Helm. Redis also has like Sentinel that you can also like just set up that way. And some users might be like, hey, you can also maybe like manually do it. But for this specific example, if you go into the primary, like if you go into primary after we ran this experiment, you saw that all the entries were gone. And then I was like, hey, maybe the replica has my entries. But nope, because Kubernetes brought that primary container back up, and when it brought that primary container back up, the 2 replicas decided to look at that primary container and wipe all the information. So that resiliency or anything with a replica just wasn't there anymore. And as an engineer, that just kind of sucks. So it would be cool to start seeing more projects and more companies start thinking about those things out of the box. And that's the cool thing. You get to battle test things with chaos engineering. So Adrian talked about the Chaos Conference talk, like the Chaos Conference that happened in San Francisco. For that one, I decided to, with my coworker, we decided to put EKS and another cloud provider, Kubernetes, just to battle. Like, hey, I'm a company trying to choose where I want to deploy Kubernetes, and I want a cloud to actually manage that part of it. So we just put them side by side, decided to shut down the Kubernetes dashboard container, and it's like, yeah, everything's gonna come back up. Kubernetes promises that everything's gonna go well. Well, that actually wasn't the case. So being able to know that right before you start developing on top of that is highly critical. It's good to think about resiliency just from the start. At Gremlin, we're trying to help the world create a more resilient internet. So with that, we've started creating a chaos engineering community. So this includes a really cool Slack that has over 2,000 folks all over the world, from companies like Amazon, Facebook, Google, Twitter, to smaller startups. Some of them have actually started running chaos engineering in production. They share their successes, their failures. Some of them are trying to get buy-in from upper management, and we have discussions about that. There's also even people that are like, hey, I've never heard of DevOps or SRE, but I'm an engineer, but I want to get into this space. Can you teach me how to get started? So that's pretty cool too. And then we've also been putting out tutorials in the DevOps SRE space over at gremlin.com/community. Some of it includes how to set up a high severity incident management inside your company, how to get buy-in from your manager to do chaos engineering, to one of our latest ones that's deploying Gremlin on ECS and being able to like run something on that. If you're interested in learning more about Gremlin, I put the link down below to get started with an enterprise trial that you're able to take home, be able to play with tonight, and maybe even also deploy the guestbook application and actually see how that actually happens. And maybe you have more free time and decide to fix the Redis replication issue and then run the experiment and actually see that your fix actually made it a lot more reliable. I'm going to turn it back to Adrian to talk about the future of chaos engineering, but I'll be back on stage after.
Cool. Thank you. Okay, that's great. So I'm going to talk a bit about some future directions, and hopefully we'll have a few minutes at the end. We'll both come back and we'll take some Q&A. So, observability of systems, right? How well can you tell what they're doing? Something about epidemic failure modes. I think this is an area that people don't necessarily understand, so I'm going to talk a little bit about that. And then automation and how we get to the future maybe of continuously running our chaos experiments. So observability. There's actually a precise definition of observability. It comes from, it's a control theory term from the early 1960s, where it was first described. Basically, if something is observable, it means by looking at the inputs and outputs, you can basically predict what it's going to do, right? There's no hidden internal state. If you ask it to do the same thing twice, it'll do the same thing the same way twice. So what that means is if you're trying to take a monolithic system and you log as much information as possible you can find about its internal state, you're trying to understand why when you ask it to do three things, it does them differently, because the logging will tell you what the internal state is. If you have tracing, now you can see the flow within your monolith, all the different order that things are happening, and you get more, it's now easier to understand how it's going to behave. Now, if you have a microservice that does one thing, and typically you just ask it to do it 10 times, it'll do the same thing 10 times. Given the same input, you should get the same output. Now, some microservices have internal state. They're a little more complex. So, you need to have some logging that's going on to tell you what's happening in that microservice. But if you look at Lambda functions, AWS Lambda functions, they typically have no side effects, right? And you could maybe construct one that's, it's not normal to create one that has some side effects, but functional programming, the idea of functional programming is you have no side effects. So if you call a Lambda function 100 times with the same input, you should always get the same output. And you don't need as much internal logging. All of what you then end up looking at is the calling patterns between your Lambda functions, which you can use something like X-ray to track, or IO pipe, something like that, to track across your different functions. So think about the observability and how that's changing. Let's look at different kinds of failures. Most people end up, just for simplicity, let's assume one thing goes wrong at a time, and I can deal with that. Okay, I'm good. Well, what happens if two things happen at once? Well, then you throw your hands up. There's just too many permutations of two different things going on at once for you to deal with. So the common assumption is let's just try and deal with one thing at a time. But quite often, there are these correlated failures where this thing breaks, it will always cause this thing next to it to break, and this thing next to it. So what happens when you have these correlated knock-on effects, and you have to think about modeling those a bit more carefully. And then finally, there's this problem with epidemic failures where everything fails at once, and people don't talk about this much, so I'm going to spend a few minutes talking about it here. Anyone remember the Linux leap second bug? Like a few years ago, hey, let's put a leap second in because the world's turning at slightly the wrong speed or whatever it is. You know, every now and again they put a leap second in, and there was a particular version of Linux where it would just stop. And if you happened to be running the wrong version of Linux, your website just stopped and your system stopped. And there were several people had a very bad day that day because large amounts of the infrastructure stopped. So this would be probably about 6-7 years ago. I remember, I think I was still at Netflix. Some of our machines were so, the kernel we were running was so old that they hadn't got the problem yet, and some of them were new enough that we got past the problem. But we lost a few EMR Hadoop clusters somewhere along the way of just trying to keep track of everything we had. We were in the middle of a major sort of kernel level update at that time. We hadn't finished getting it done. So that's one problem. Back in the 1990s, I used to work for Sun, and we shipped hardware where there was a problem where every now and again one of the bits in the cache would flip and the machine would crash. We found this out after we'd shipped rather a lot of hardware. That wasn't a good experience. If you have a cloud zone or region failure, that's also an epidemic example. It doesn't matter what you were running, if that zone goes offline, then everything in that zone is gone. That's an epidemic failure. DNS failure, as I mentioned earlier, just forgetting to renew your DNS or all kinds of DNS problems. It's actually it's probably the soft underbelly of most systems. If you can get at the DNS for a system, you can break it. It's pretty easy to do. And then there's the whole security configuration, leave off a semicolon in some file and deploy it globally and then watch everything collapse, that kind of thing. I've seen a few examples of that happen over the years. Somebody was tweeting a talk I gave years ago, and they said to fail is human, but to fail and deploy it globally simultaneously is DevOps. It was something like that. So be careful what you're doing with your automation, right? So when you have an epidemic, you need quarantine. Right? If you ever travel and there's an epidemic like the SARS epidemic, you see people wearing face masks on planes, and then if you go, particularly in Asia, as you come through the airports, they have scanners which are looking for people with high temperatures. They're doing infrared scanning of people coming in, and if you're running a temperature, they'll pull you aside because they want to make sure that they don't let the sort of flu epidemic spread through their airports. So quarantine's an interesting point. So how do you quarantine these things? Well, one way to quarantine a Linux kernel bug maybe is to run on other operating systems as well. Maybe you're deploying your Java application, and you could deploy it on Windows. It should still work, right? So maybe you figure out as a backup, just in case anything goes wrong with Linux, what's the code base that's most different from Linux that still runs most of the things you want? And it's probably Windows. So maybe you can run Windows as a backup for some of your most critical applications. Sort of think about that, or maybe BSD or something, or a totally different version of Linux. But you want something with a more diverse code base. Variety of CPU implementations. If you are completely homogeneous, you have exactly the same type of CPU, the same Intel chip, the same whatever chip. If there's a problem with one of those, then everything goes at once, right? Cloud zones. You should be using cross-zone, cross-region replication to make sure you're not dependent on any one zone. And then DNS. It's good practice to have more than one DNS provider so that you can fail over providers, and also to have multiple domains so that you're not running everything through a single domain. You have a domains for production, maybe is separate from your domain for your corporate email, things like that. So there's ways you can spread the risk around. And then limit the scope of deployments. The way that AWS does its deployments is a zone at a time, a region at a time, stand back, does that look good? Okay, we'll roll it out. So anything that looks like a security change or a network change is deployed very, very carefully, and you walk them through. Now, staging that manually can be a pain. There are some products out there, there are some services out there that will help you do that. So roll your workloads across your production infrastructure using things like canary testing and use code pipeline or Spinnaker or something like that. So you've got to manage it to contain the epidemic. And the nice thing about this, though, is cloud now gives you the automation that's leading to chaos engineering. One of the reasons why disaster recovery has been so hard in the past is that the disaster recovery failover to the other data center, you're never quite sure that that data center is in the right state to run this workload that you've got here. So if I'm going to fail it over, and I think everything's in the right state, but it turns out, oh, we've got a downrev firmware here, and this network's not quite in the right state, and they drift independently. The thing about cloud is it's much easier to contain that. Basically, the APIs and the services in 2 regions or 2 zones are effectively identical, and you can run CloudWatch logs and things like that to basically be sure that you've got exactly the same configuration everywhere. So that automation is one of the things that that's sort of an answer to why is chaos engineering happening now? And I think it's because cloud is giving us the ability to automate disaster recovery in a low-cost, repeatable, productizable way, rather than having disaster recovery be an extremely custom, expensive, hand-built, bespoke thing, which you have to recreate and everyone's scared to test, right? So it's this level of automation consistency that really makes it possible. And I think we're going to, as we see these data centers migrate to cloud, we're going to start seeing chaos engineering replacing the manual disaster recovery processes that we've had in the past. And it's going to move from being a scary annual experience that's provoked by the auditors turning up to something that you do continuously in your production systems. You know, I left Netflix 5 years ago, but we were doing quarterly tests at that time. They now do it every few weeks, and they've automated their systems, so they do zone and region level testing and lots of internal tests. Thousands of tests a day are running continuously. You'll probably hear some talks about this later this week. But there's a huge amount of work goes into getting that done, and it's been years of work for Netflix to get to that point. So that's kind of like a existence proof. It's possible to get there. Most people are at a much earlier stage, but I think this is the trend we're looking at. And the more critical your application, the more we're interested in figuring out how we can build the right products and services from AWS and our partners like Gremlin. How can we help you build systems that are more resilient? If you're working on something right now that is absolutely critical, health, safety, or business critical, talk to us, particularly let me know I'm interested in these workloads and figuring out, do we have all the right things to support you in it? So thanks for that, and bring Anna back up. We have a few minutes left for some questions. Any Q&A? Everyone just desperate to get out and get some more coffee.
Time to do a line for like the next container talk, basically.
So it's good to have 2 presenters, by the way. This is a highly resilient system. If one of us didn't turn up, the other one could have taken the deck. So, did you see any comments on Twitter to highlight?
Nope, just someone asked about the books and got them the list of books that you mentioned earlier.
Yeah, I mean, if you want, like I said, if you want to find these talks in more detail, particularly if you want more detail on my talk, I have about twice as much content in the talk I did at the Chaos Conference, which I think there's links to that from the Gremlin site.
Yeah,
they were running
they're also on YouTube. You can look up Chaos Conf, like Anna Medina, Adrian, and you can load up the videos there. And I'm also around the rest of the week if you have any questions on chaos engineering or Gremlin or just having fun breaking containers.
Right. Okay. Well, thanks, everybody. Appreciate it. Have a great week.